In this session, we're going to work the problems in the Chapter 2 review, starting with problem number 1. Here we have conditional statements that we need to write. Write the if-then form, the converse, the inverse, the contrapositive, and the biconditional of the statement. So, for problem 1 it says, two lines intersect in a point. The if-then form of this can be, if two lines intersect, then they intersect in a point. So we take the subject and the object. For the converse, we take the hypothesis, swap it for the conclusion. So the conclusion goes where the hypothesis is, the hypothesis goes where the conclusion is. The converse of this statement is rather redundant. It says, if two lines intersect in a point, then the lines intersect. It sounds kind of pointless to say. However, we take the conclusion, move it to the hypothesis, take the hypothesis, move it to the conclusion. And now for the inverse. With the inverse, we negate the hypothesis of the if-then, and we negate the conclusion. So, if two lines do not intersect, then they do not intersect at a point. Negation means to take the negative of, or not. And now for the contrapositive. With the contrapositive, we take the converse of the inverse, or the inverse of the converse. In other words, we take the hypothesis, move it to the conclusion, and negate it. Take the conclusion of the if-then, move it to the hypothesis, and negate it. So we have, if two lines do not intersect at a point, then they do not intersect. So we took the conclusion, negated it, took the hypothesis, negated it. And now for the biconditional. A biconditional requires that the if-then be a true statement and that the converse be a true statement. In this case, they're both true. And so the easiest way to form a biconditional is to take the hypothesis of the if-then, insert the phrase if and only if, and finally put the conclusion of the if-then. So, two lines intersect if and only if they intersect in a point. And now let's do problem 2. In problem 2, I'm going to take the liberty of disagreeing with the author's conclusion. In English, this statement, 4x plus 9 equals 21 because x equals 3, the because statement is giving us a condition. X equals 3 causes 4x plus 9 to equal 21. And I understand what they're trying to say, but the way this question is worded, the interpretation that I make is, this is the condition, this is the conclusion. So, my if-then statement is, if x equals 3, then 4x plus 9 equals 21. So just to clarify, in my opinion, a better phrasing of this problem would have been, x equals 3 because 4x plus 9 equals 21. In this case, this would have been the condition, this would have been the conclusion, and that would have been more proper for this kind of mathematical statement. However, just for the sake of looking through if-then statements, we're going to use this interpretation as we move forward with the rest of the statements. So for the converse, we take the conclusion, it becomes the hypothesis. We take the hypothesis, it becomes the conclusion. So the converse is, if 4x plus 9 equals 21, then x equals 3. And now for the inverse. For the inverse, we negate the hypothesis. If x does not equal 3, then, and then we negate the conclusion. 4x plus 9 does not equal 21. Now for the contrapositive. And for the contrapositive, we take the converse of the inverse or the inverse of the converse. In this case, I'm going to take the converse of the inverse. So we take the conclusion of the inverse, we make it the hypothesis, take the hypothesis of the inverse, make it the conclusion. So contrapositive, if 4x plus 9 doesn't equal 21, then x doesn't equal 3. Going back to the original conditional, it's the negative of the conclusion, negative of the hypothesis. And now for problem 3. In problem 3, it's fairly straightforward. The subject is up front, the conclusion is in the back. So the if-then form, if angles are supplementary, then they sum to 180 degrees. Now the converse. For the converse, I had to add a word. If two angles sum to 180 degrees, then they are supplementary. And that was only because the definition of supplementary angles is two angles whose sum is 180 degrees. So we take the conclusion, it becomes the hypothesis becomes the conclusion. And now for the inverse. So we go back to the original if-then statement and we negate the hypothesis and negate the conclusion. If angles are not supplementary, then they do not sum to 180 degrees. And finally the contrapositive for the if-thens. And we take the conclusion, it becomes the hypothesis negated. If two angles do not sum to 180 degrees, then we take the hypothesis and negate it. They are not supplementary. So that's the contrapositive. Now for the biconditional. The biconditional, we take the hypothesis, insert the phrase if and only if, followed by the conclusion. So two angles are supplementary if and only if they sum to 180 degrees. And now on to problem 4. In problem 4, again, fairly straightforward. If an angle is a right angle, then it measures 90 degrees. So now for the converse. For the converse, we take the conclusion, make it the hypothesis, make it the conclusion. If an angle measures 90 degrees, then it is a right angle. Now for the inverse. So now we negate the hypothesis, negate the conclusion. If an angle is not a right angle, then it does not measure 90 degrees. And contrapositive. And for the contrapositive, we negate the conclusion, make it the hypothesis, negate the hypothesis, make it the conclusion. If an angle does not measure 90 degrees, then it is not a right angle. And finally, the biconditional. For the biconditional, we take the hypothesis, an angle is a right angle, insert the phrase if and only if, followed by the conclusion. It measures 90 degrees. We could have swapped these by saying an angle measures 90 degrees if and only if it is a right angle, but the easiest way to do it is hypothesis, if and only if, conclusion. And now on to problem 5. Problem 5 says, what conclusion can you make about the difference of any two odd integers? In this problem, we're going to use some inductive reasoning to draw a conclusion. That is, we're going to make some observations and draw a general conclusion from those observations. So let's take the difference of a couple of odd integers. So let's start with 9 minus 3 equals 6. Then let's do 7 minus 5. That equals 2. And 3 minus 5. That equals negative 2. The conclusion I can make here is that they produce an even integer. So that'll be our conclusion. The conclusion we can make about the difference of any two odd integers is that they produce an even integer. Okay, now on to problem 6. Problem 6 asks us, what conclusion can you make about the product of an even and an odd integer? Again, we're going to do some inductive reasoning. So let's do 3 attempts here to generate a pattern. So let's do 2 times 3. That equals 6. Let's multiply -5 times 2. That equals -10. And then let's do 4 times 5. That equals 20. So again, I think we can make the conclusion here that the result is going to be a positive integer. So here's our conclusion. The product of an even and an odd integer is an even integer. Now on to problem 7. Problem 7 says, use the law of detachment to make a valid conclusion. Our conditional is, if an angle is a right angle, then the angle measures 90 degrees. Our fact is that angle B is a right angle. Now, for the law of detachment to apply, this conditional must be true. And so we have, if an angle is a right angle, then the angle measures 90 degrees. That is a true conditional. The fact says angle B is a right angle. The second condition of law of detachment is that the hypothesis of the true conditional must be true. This fact tells us that that hypothesis is true. Therefore, the law of detachment applies, and our conclusion is the angle measures 90 degrees. For a more detailed discussion of the law of detachment, check out the video that I have in this chapter on the law of detachment, also with the law of syllogism. And now on to problem 8. This problem asks us to use the law of syllogism to write a new conditional statement that follows from the pair of true statements. If x equals 3, then 2x equals 6. If 4x equals 12, then x equals 3. Now in the law of syllogism, what we're looking for is a repeating statement, because the general form of law of syllogism is if A then B, and if B then C, therefore if A then C. And so we're looking for this repeating piece, this conclusion of the first statement, which becomes the hypothesis of the second. So here we have a conclusion that is repeated in the hypothesis of the first. So our actual condition is if A, then B, if B, then C. So our final statement would be if A, then C. And so our conclusion would be if 4x equals 12, then 2x equals 6. For a more detailed description of the law of syllogism, check out the video that I produced in this chapter, along with the video on law of detachment, as I described in the previous problem. And now on to problem 9.